Hi everybody, welcome back. Let's do our first correlation and regression example. Now keep in mind, in order to do regression, we need a lot of the information that we get when we compute a correlation. The two analyses go hand in hand. So to do this regression analysis, we're going to start by doing a correlational analysis. I know that we've done this previously together, so I'm going to go through this one pretty quickly. You'll of course want to work the whole thing out by hand using your handout. Take your time. You can always pause this video. I'm though just going to highlight some of the things that are most important along the way for each step and some of the mathematical stuff that I know some students get tripped up on. So let's go through this. It says, examine the following data and compute a Pearson's correlation coefficient. Is there evidence the two variables are related in the population? In other words, is the sample correlation significantly different from zero using a two-tailed test and an alpha of 0.05. All right, we've used high school GPA and college GPA in the past. We'll use it again. So it's just an example because we want to learn how to go through the steps. All right, so the null hypothesis, of course, is that the population correlation, rho, kind of looks like a P. It's a Greek letter rho, R-H-O, equals 0. If the correlation equals 0, it means there's no relationship between the two variables in that population. And of course, if we're doing a two-tailed test, the alternative is going to be that rho is something other than 0. Step 2 is all about figuring out how much evidence we need to reject that null hypothesis. So we need to figure out where our critical region is. If you'd like, you can draw a distribution and then mark off these critical regions. I'm just going to list the critical values. Keep in mind the critical values are based on the number of people or things we've measured. And we've measured 2, 4, 6, 8 different people here. So if n equals 8, n minus 2 would equal 6 degrees of freedom. Let's look that up real quickly. We are doing a two-tailed test. We're using an alpha of 0.05, and we have 6 degrees of freedom. So I'm going to come across this row. I'm going to stop at this column. That value right there represents our critical value, plus and minus 0.707 for this correlational analysis. So let's go back, and we've got that listed right here. I gave us a little bit of room here to sketch a scatter plot. This is something that's not completely necessary for a correlational analysis, but I always think it's smart. Remember, we typically have our x variable, our predictor variable, on that x-axis, and our y variable, the criterion variable, on the y-axis. And our predictor variable clearly is high school GPA. We will use people's high school GPAs to predict their college GPAs. At this point, just go ahead and fill in the scatter plot. For each one of these 8 people, just plot their position in that two-dimensional space. This first person has a high school GPA of 1 and a college GPA of 1.5, and you can locate that right there, right below that hand on the scatter plot. And you'll want to do it for the rest of them. So like that last person had a high school GPA of 4, college GPA of 4. Here's 4 for high school and 4 for college. So when I look at that, I can now make a preliminary estimate of R. In other words, I can just look at the data and then guess what my R coefficient might equal. You can see that's clearly a positive correlation. We're heading from the lower left to the upper right. And if you were to draw like an imaginary straight line, best fitting these data points, you'd see that those data points are going to be pretty darn close to that line. In other words, that's a really strong positive correlation. So let's make an estimate of the R value. I would estimate that this is an extremely strong positive correlation, maybe a correlation coefficient equal to about 0.95. So go ahead and write over here R equals 0.95. And just to make it clear that this is our estimate, above the R, put a little caret, a little hat on it. That typically represents estimated or predicted R value. All right, so step 2 is done. Let's go ahead to step 3. Step 2 was all about figuring out how much evidence we need to reject the null hypothesis. Step 3 is all about figuring out how much evidence we actually have. So I created columns here for x and y. This is just my data. And I know by looking at these formulas, I need an x squared value, the sum of all the squared x values. So I created a column for x squared. I can see in this formula right here, I'm going to need the sum of the squared y values. So I created a column for y squared. And I can see right here, I'm going to need the sum of the x's times the y's. So I created a column of x times y. Once you find all those values, just sum up each column. Now we know the sum of x, the sum of y, the sum of x squared, the sum of y squared, and the sum of x times y. And that's everything that we need to compute these three formulas right here. Once we have the sum of squares x, which is a measurement of variability for the x variable, and once we have the sum of squares y, which is a measurement of variability for the y variable, and once we have the sum of the products of the deviation scores, which is a measurement of how they co-vary together, then we can finally compute that standardized R coefficient. Remember, those values need to range between -1 and 1, where 0 represents no relationship between the two variables. All we need to do now is plug in those three values into this equation. Let's go ahead and walk through the computations together. Be careful with this formula right here. It tells us to take the sum of squares for the x variable, multiply by the sum of squares for the y variable, and then once we find that product, we need to make sure we take the square root of it. So we have 8.77, that's the sum of squares x. We're going to multiply that by the sum of squares y, which we can see is 5.62. That equals about 49.28, actually about 49.29. So remember, a little bit of rounding is no big deal for our class. We want to take things one step at a time so everybody can follow along. So now I'm just going to take the square root of 49.29. And that equals 7.02. So we see now we're right over here. So we take the sum of the products, 6.34, divide by 7.02. And before I hit enter, I just remind myself I'm expecting a large positive correlation, something somewhere around 0.95. I hit enter and I see I find a correlation coefficient of 0.90. So it's in the right ballpark. That is a strong positive correlation. So I'm feeling confident about my calculations. My calculations are very close to what I estimated from the scatter plot. Let's go ahead now and make a decision about the null hypothesis. Do we have enough evidence to reject the null hypothesis? Let's first figure out if our obtained R value is within the critical region. Critical regions start off at 0.707 on the positive and the negative side. We found an obtained R value of 0.90, so we are clearly inside the critical region. Of course, we call that critical region a rejection zone. So our first question is, are we inside the rejection zone? Yes, we are. All of the follow-up questions should have that same response, yes. Should we reject the null hypothesis? Yes, we should. Go ahead and X that out. That means we're going to embrace the alternative. The alternative says there is a relationship in the population between those two variables. The population correlation is not 0. And we have evidence to show that it's a strong positive correlation. Our next follow-up question is, do we have statistically significant results? Yes, we do. Is it possible that we're making a type 1 error? Yes, it is at least theoretically possible. What is the probability? We're using an alpha of 0.05, so theoretically speaking, over the long run, the probability is 5% that we will be making type 1 errors in this type of situation. Let's discuss the P issue real quickly. We're going to have to decide if the probability of finding our results just by chance is less than 5% or greater than 5%. We found that our obtained R value was inside that small critical region, so our probability should be associated with a small value. What's small? A probability less than 5% or a probability greater than 5%? Of course, what is small is a probability of less than 5%. So go ahead and just jot down a little note to yourself. That's how we will write up our results. Let's go ahead and do that in step 4. In step 4, we just formalize everything we just said. Our R statistic is in the critical region, and this is very unlikely if the null hypothesis is true. In fact, it's so unlikely we start to question the null hypothesis, and ultimately we decide to reject it. The two variables, high school GPA and college GPA, are positively related in the population. How would we write that up? In a journal article, we would say that R with 6 degrees of freedom equals 0.90, and the probability of finding that just by chance is less than 5% based on a two-tailed test. The appropriate measurement of effect size is R squared. all we need to do is take that R value, 0.90, and square it. Let's go ahead and do that. So I'm going to punch in 0.90, hit my square button, and that equals 0.81. What we're learning from that is that 81% of the variability that we see in college GPAs can be explained by high school GPAs. 81% of the variability in the criterion variable, college GPA, can be explained by the variability in our predictor variable, high school GPA. Now we have pretty much all the information that we need to do our regression analysis. Step 5 asks us to compute the slope, which is b, and the y-intercept, which is a, so that we can obtain the best fitting straight line for the data. So take a look at that regression equation. What we're trying to do is predict college GPA. GPA is the criterion variable. It's the y variable. We see y hat because that represents a predicted college GPA. And how are we going to find that predicted college GPA? We're going to take their high school GPA, which is X, multiply it by that B value, the B weight, that's the slope, and then add A, which is our y-intercept value. So clearly what we need to figure out is what's the value of the slope and what's the value of the y-intercept. Smartest thing to do is just look at your formulas. In order to compute that B value, the slope, we need the sum of the products and we need the sum of squares X. We can get that information from our correlational analysis that we just completed. Let's look at our formula for A. That's based on computing the mean of y and the mean of x, which we'll need to do real quickly. And it's also based on knowing b, the slope. So do you see how it makes sense to compute the slope first? We're going to need that value of b for this formula right here for a. So that tells me exactly where to begin. I want to begin by computing the slope. So you can look back on the previous page. You'll see the sum of the products was equal to 6.34. The sum of squares x was equal to 8.77. Let's just crunch those numbers real quickly. 6.34 divided by 8.77 does indeed equal 0.72. Let's ask ourselves if that makes sense. We found a positive correlation between the two variables. The slope is positive, and the value that we just computed for the slope is a positive value, so at least that makes sense. Let's move on to the y-intercept. The y-intercept uses the symbol A, the letter A in the equation for it. So in order to compute it, we need to know the mean of y, we need to know the slope, we have that now, and we need to know the mean of x. Let's go ahead and compute the mean of y and the mean of x real quickly. Okay, I'm just going to go back to our raw data here, where we already computed the sum of x and the sum of y. Let's take the sum of x, which is 20.5, and then compute the mean. We'll divide by 2, 4, 6, 8 people. All right, so that mean is about 2.56. You can just jot that down. Let's go ahead and compute the mean of y. The sum of y is 22.5. Of course, we're going to need to divide that by 8 people. That equals about 2.81. Go ahead and jot that down as well. Here we are back to computing our value for A. I've stuck in the value for the mean of y, 2.81, minus the slope, 0.72, which we just computed above, multiplied by the mean of x, which is 2.56. Let's just work it out real quickly. We have 2.81, which just follows us down. Now we want to multiply 0.72 times 2.56. So take 0.72 and multiply by 2.56. That equals about 1.84. So now we're left with 2.81 minus 1.84. So the math involved here is pretty easy. The y-intercept equals 0.97. Remember, the y-intercept is the point at which that line, that regression line, crosses the y-axis. Said yet another way, if somebody had a high school GPA of 0, this equation would be predicting that they would have a college GPA of 0.97. Now we can go ahead and write out our full regression equation. Predicted y equals b times x, the slope 0.72 times x plus our y-intercept 0.97. Now, in order to find any predicted college value, all we have to do is take 0.72, multiply by their high school GPA, and add 0.97. We know all of these people's high school GPAs and their actual college GPAs. Let's see how well our regression equation would predict their college GPA. So what we're going to do is take their high school GPA and plug it into our regression equation, and then we'll see what the equation would predict. Let's start with that first person. We're going to take 0.72. We're going to multiply by their high school GPA, which was 1. That equals 0.72. Now we need to add to that 0.97. So we would predict that that person would earn a GPA of 1.69 in college. They actually earned a GPA of 1.5. So it's doing pretty well. Remember, we had a really strong correlation in this example. When two variables are related very strongly, we should be able to use the data from one variable to predict the other variable very well. Let's do another, and then you can do the rest. The next person has a high school GPA of 1.5. So we're going to take 0.72. We're going to multiply that by 1.5. That equals 1.08. We need to add now 0.97. So if someone has a high school GPA of 1.5, we predict that they will have a college GPA of 2.05. This person actually had a college GPA of 2.0. So our regression equation is actually performing really well. Let's just do one more. This next person has a high school GPA of 2. Let's take 0.72, multiply by their high school GPA, which is 2, and then add to that 0.97. So we would predict that those people who earn 2s in high school would earn a 2.41 in college. This particular person earned a 2.0 in college. So this particular prediction isn't quite as close as the ones we saw previously, but it's also not all that far away. In this case, it's within half a grade. Go ahead and do that for the remaining values. Let's just go through this last one together. Assume that someone had a GPA in high school of 4. We're going to take 0.72, multiply by 4, and then add to that 0.97. So we would predict they would have a college GPA of 3.85. Take some time to compute the rest of these predicted values if you haven't already. But right now, let's go ahead and plot that regression line. I'm going to show you how to do it. In order to plot any line, we need 2 points. Once we have 2 points, we'll just connect those 2 points. I like those points to be relatively far away from each other because when they are, it's just easier to draw a more accurate straight line. So one value that I always like to use is the y-intercept. So I'm just going to use the value where x equals 0 and plug that into my equation. So if x equals 0, 0.72 times 0 equals 0, and then we're going to add 0.97. So that leaves us with a data point located with an x value of 0 and a y value of 0.97, which is right where you see that big dot below this hand. So there's one of our data points. That is right there, the y-intercept. Now I'd like to plot another point that's relatively far away. So let's assume that somebody has a high school GPA of 4. We already walked through the math for that. This person had a high school GPA of 4. When we put that into our regression equation, we found a predicted college GPA of 3.85. So 4 would be right here on the x-axis below me, and 3.85 would be right about here as well. So I plotted this big black dot right here. Now that I've got those 2 points labeled, I just simply connect the dots with my line. That, my friends, right there is the regression line. That is the best fitting line for our data. That line comes as close as possible to as many data points as possible. The last thing I want to compute is the standard error of the estimate. The standard error of the estimate is essentially the standard deviation, measuring how much these points deviate from that regression line. The more they deviate from that regression line, the less well our regression equation does at predicting college GPAs. So it's a good overall estimate of the overall health of that regression equation. Let's look at the equation and see what we're going to need. So here's our equation right here, right underneath that hand. It shows that we're going to need S sub y. S is always standard deviation. That's just the standard deviation for the y variable. So we're going to have to compute that. We're going to need to have the r squared value. That's no problem. We already know r. And we also need to know n. So, and what it looks like we're going to need to compute first is the standard deviation for the y variable, because we don't have that information yet. So let's compute that next. So here's the formula that we're going to need. Remember, a standard deviation is simply the square root of variance. The formula for variance, you can check any of your formula sheets, is just sum of squares divided by n minus 1. Well, I need the square root of that. That will give me the standard deviation for the y variable. So let's go back and look at our data real quickly. We should have the sum of squares for y. So I'm going to move back, and I'm going to look at sum of squares for y. It equals 5.62. So in my equation, I'm going to take 5.62 and divide by n minus 1. We can remind ourselves that we have 2, 4, 6, 8 pieces of information. We have an n of 8. 8 minus 1 is 7. So we're left with 5.62 divided by 7. Let's crunch that real quickly. 5.62 divided by 7 equals about 0.80. Remember, just a little bit of rounding as we go is no big deal. It helps us take things one step at a time. So type in 0.80 and hit your square root key. About 0.89. Now that we know the standard deviation for y, which is right there below the hand, we can stick that into our equation, 0.89. Underneath this radical sign, we need in parentheses there 1 minus r squared. Let's go back and remind ourselves what r equals, and then we'll be able to figure out 1 minus r squared. R equals 0.90. That's right here. All right, we can use that. So let's figure out what we need right there in those parentheses. 1 minus r squared. So let's figure out r squared first. If r equals 0.90, we just need to square that. That equals 0.81. So in order to find 1 minus r squared, we'll just take 1 minus 0.81. That equals 0.19. That's where this value comes right here. This part of the formula is asking for n minus 1 divided by n minus 2. Our n equals 8. So we're going to need 8 minus 1, which is 7, divided by 8 minus 2, which is 6. 7 divided by 6. 7 divided by 6 equals 1.17. So that's where this value comes from right here, 1.17. Let's just go ahead and continue with the mathematics that are needed. Let's work underneath that radical sign first. We're going to take 0.19 and multiply that by 1.17. That equals about 0.22. So if you want, you can round it to 0.22. And then just take the square root of that. Square root of that is about 0.469 or about 0.47. And that's where we get this value right here. So finally, in order to finally finish this equation, we need 0.89 multiplied by 0.47. And that equals about 0.42. All right, that, my friends, is the standard error of the estimate. So that represents the standard deviation of the points surrounding that regression line. So one way you can view it is that, on average, our predicted values differ from our actual values by about 0.42. And when we're talking about GPA, that means our predicted values are off from the actual values by about half a grade. I hope this example was helpful to you. We got a little bit more experience doing a correlational analysis, and this was our first chance to do a full regression analysis. You can see just looking at this page here on the left, there's not all that much that we actually need to do, and the math is relatively easy. Computing standard error of the estimate is a little bit of a pain, but that's not such a big deal either. Just take your time with it. In the next video, we'll go through a second example, where again, we'll have to compute a correlational analysis, and then we'll compute a regression analysis. They are all the same, my friends. All I can do is give you different numbers. So just go through the steps, make sure you understand each step, and you understand the mathematics involved. If you have any questions, just ask me or one of the tutors. If you practice this, you're gonna master it. You can definitely do this. I'll see you in the next video.